Alright, everybody. Chapter 5, who is excited? This guy. Alright, let's get this done quick so I can go back to my Big Bang Theory marathon. 5.1, using fundamental identities. 3, 2, 1, boom. Basically what we're going to be doing here is using these identities to try and solve for different values, whether I'm given sine and I want to find the cosine tangent or cotangent, or using these identities to try and rewrite trigonometric expressions. Alright, so we're going even farther. We're not looking at these things as ratios, we're not looking at them as functions, we're now looking at full-on expressions of these trig functions. Alrighty, so that's what we're doing. Let's take a look and recap the fundamental identities, the things that we've seen before. First of all, the reciprocal identities, that sine is the same thing as 1 over cosecant, that those two are reciprocals of each other. Same thing here, cosecant is the same thing as 1 over sine. They are reciprocal. Right? So these two are related. That cosine and secant are related with that same reciprocity, and that tangent and cotangent are related in the same way. The second category is the quotient identities, which is just understanding that tangent is sine over cosine, cotangent being its reciprocal, tangent to cotangent, that instead of sine over cosine, it would be cosine over sine. Alright, and then our last set of identities are the Pythagorean identities. They come directly from a squared plus b squared equals c squared. And that's exactly what this is. Sine squared plus cosine squared equals 1, because the radius of the unit circle is 1. And then these two are found simply by dividing the entire equation by cosine and dividing the entire equation by sine. That was something that I had challenged you to do before, and hopefully some of you have gotten that. Alrighty, let's see how we can use these things to help us when we're looking at trig expressions. There's also some other ones. We're not going to focus too much on these, the cofunction and the even odd. They are very important relationships, and we'll look at them, I think, in a couple of sections. But these are different identities that, again, we already kind of know in a way, we just haven't really put them into such a formal manner. The even odd ones are probably the ones that are the simplest. It's just the idea that the sine function happens to be an odd function, and so putting in a negative value there turns the entire function negative. The cosine is an even function, so the negative value of anything just keeps the function regular. Tangent function is odd, changes it. Cosecant function is odd, changes it. Secant function is even, so it stays the same. And the cotangent function is odd. I had mentioned this a lot earlier in the year, that of the 6, 4 out of 6 are odd, and only 2 of them are even, and those 2 are the secant, cosine. Those 2 go together, being even. The cofunction identities come from the idea of I think maybe 2-3 sections back, we focused on trying to find reference angles. And these are just a way of formalizing the idea of reference angles. Alright, so let's use them. I am given that the secant of u equals -3 over 2, and that the tangent of u is greater than 0. Find all 6 trig function values. Okay, so I can first off see how this is important. I can't really see why that matters, first off, just looking at it. So in a way, I'm a little bit confused because I'm not quite sure what to do, but I do know that there's one thing for certain. I know that the cosine of a specific angle is supposed to be 1 over the secant. So that should be something easy that I can get. That would mean that it's the reciprocal of this whole thing. So it should be -2 over 3. So the cosine should be -2 over 3. Cool, I got one of them. Now, I do believe we did an example way back where I had cosine and I wanted to find sine. It was a bit of a stretch on how to get there, but we can use one of these identities to do that pretty easily. One of them says sine squared plus cosine squared equals 1. Now, if I were to rearrange that so that the sine is by itself, sine squared equals 1 minus cosine squared, now I can solve for sine just by taking the square root. All right, so I'm going to do that the sine is equal to square root of, I'm going to go ahead and leave this sine squared.
Check that out.
Say 1 minus the cosine squared, which is negative 2 over 3 squared, and that's going to be 1 minus 4 over 9, which equals 5 over 9, which is sine squared, which means that the sine of u equals the square root of 5 over 3. Cool. Now that I have that, I can find tangent, right? Because sine over cosine is tangent. Tangent equals sine over cosine, which in this case, sine is square root of 5 over 3, which is going to be over negative 2 over 3. Again, fractions are super important. So that's going to be the same thing as square root of 5 over 3 times negative 3 over 2, which gets me the square root, when these two things cross off, of 5 over 2. So my tangent is the square root of 5 over 2. I'm going to start circling things so I don't get confused. Cosine, sine, tangent. Beautiful! Next, cosecant. Well, actually, for the rest of all these things, it's super simple because all I'm doing is reciprocals. The cosecant, the reciprocal of the sine, it's going to be 3 over the square root of 5. Rationalize that denominator. I'm going to get 3 square roots of 5 over 5. Beautiful. And then the secant I already know from the beginning. And cotangent is my last one. Cotangent is going to be the reciprocal of this one, which is 2 over the square root of 5. I gotta rationalize that denominator, so 2 square roots of 5 over 5. Beautiful. And that's how we use the identities to try and evaluate for all of the different trigonometric functions. All right, it's just taking piece by piece and breaking it down. A lot of it is reciprocal identity. The next part that I want to do is simplifying equations or expressions that use trigonometric functions by using these identities. All right, this is where things start to slow down a little bit because they become more complex. You need to hold a lot of information about the identities and about the functions in your mind in order to work with it. That's really the hardest part. The algebra is not difficult. The algebra you know how to do. It's a matter of what can I substitute, this function for in order to make it simpler. So the first way that I want to look at it is by factoring a little bit. I have two different terms here. I mean, this might look really complex and really complicated, but I have two terms, each involving the sine of x. Now, if I were to take out the sine of x from both terms, what I'm left with is cosine squared of x minus 1. So now, all I've done is factor out sine of x. But I've made it a lot simpler because in here, if I can recognize it, there is a trigonometric identity in there. And that is sine squared. We actually just used that in the last page. And that's still being multiplied by sine x. And when I actually do multiply those things together, this whole thing simplifies down to the sine of x cubed. Alrighty? So that's my first example. Going from something that looks, a lot more difficult down to sine cubed of x, simply by factoring out and rewriting. Let's take a look at a different one. All three of these involve factoring in some way. And factoring, is difficult for some people just in algebra in general. But when it comes to trig factoring, it becomes like a whole new monster. So, I just want to emphasize the fact that it is the same as in algebra, despite the fact that these things look a little bit different. Okay, so what I have here for my first one is secant squared of theta, or x, minus 1, which, if you can remember some of the special cases of factoring, this is the difference of two squares that we're really looking at here. It's almost the same thing as x squared minus 1. If I had that, I would break it down into x minus 1 and x plus 1. That's what would bring me there. So the same rules are going to apply here. I'm going to get secant of x minus 1 and secant of x plus 1. Right? If you need to rewrite the trig in terms of variables, go for it. Why not? If that's what makes it work for you, then have at it. It's a popular technique. It's basically called u substitution. Generally, you're substituting in a variable of u. So in this case, let's just say I use u substitution and I transfer this to say 4u squared plus u minus 3. Essentially what I'm saying is that u equals tangent of theta. So every place that I see a u here, it's actually tangent of theta. That way I can kind of look at this and see it in a simpler way. So I'm not so confused, I'm not so bogged down by the trig, and I can work on simplifying with the algebra. So basically when this factors down, what we're going to get is 4u minus 3 and u plus 1. And then I can substitute back in that u. 4 tangents of theta minus 3 and tangent of theta plus 1. And lastly, this is the most complex factoring one that we have on here, mainly because I have cosecant squared minus cotangent of x minus 3. So I'm looking at two different things. If I tried to substitute, I would have to use two different variables, one that represented cosecant and one that represented cotangent. So the first thing that I need to do before I can worry about trying to factor or anything is try to substitute something into this equation to make it so that I'm dealing with all one function. I only want to be dealing with cosecants, or I only want to be dealing with cotangents, but I only want to work with one. Big thing I want to look for is something with a squared value, because I know that there's these trig identities, that these Pythagorean identities that show me how to twist things around using cosecant. So there is one that says cosecant squared equals 1 plus cotangent squared, which is going to be very helpful, because now I can say instead of this part, I'm going to instead substitute it for that. 1 plus cotangent squared, that's going to get substituted, and then the rest is still going to be here, minus cotangent of x minus 3. And now I can combine like terms. I'm going to have a negative 3 over here combining with the 1. So that's going to be cotangent squared minus cotangent of x minus 2. Now that I have all that set up, all I have to do is factor, which if I need to substitute, I can say cotangents are actually x's, so that's x squared minus x minus 2. How do I factor something like that? And it seems, and it looks a lot simpler, and it's something that I can really wrap my head around. So the factored form of this entire thing is going to look like x minus 2 and x plus 1. So in this case, it would look like cotangent minus 2 and cotangent plus 1. Very good. Very good.
Don't be distracted by
Last
my fancy
one
hat.
is taking something that's in fractional form and rewriting it so that it's no longer in fractional form. So what we have to do here is a little something that hopefully you would remember from working with imaginary numbers, possibly, or complex numbers. That's pretty much it. But it's called multiplying by the conjugate. So what I have here is 1 over 1 plus the sine of x, and in order to change this around or do something of meaning with it, I have to multiply, because it's a fraction, the top and the bottom by the same thing, and the only thing that's really going to move things along for me is multiplying by 1 minus sine of x, which is the conjugate of 1 plus sine of x. Because I'm multiplying both the top and the bottom, I'm essentially multiplying the fraction by 1, which does not change its value, it simply makes it look different. All right, so on the bottom, we have something nice come out there. If I multiply, I do first, outer, inner, last. The middle terms are going to cancel. It's going to be a positive sine x and a negative sine x, which are going to cancel out. And what I'm left with on the bottom is going to be 1 minus sine squared of x. On the top, is just 1 times this whole thing, so it's just that whole thing, 1 minus sine of x. Now, some of you might be a little bit ahead of me here, and you might be saying, okay, I know there's a sine squared there, and sine squared with a 1. There's got to be something there to do with a Pythagorean identity. And there, in fact, is. If I keep the numerator by itself, 1 minus sine x, I can change the denominator to be a cosine squared of x, which is going to make things a lot simpler for me because it's just one number in the denominator, and I can now break up the fraction into 1 over cosine squared of x, which is there, minus sine of x over cosine squared of x. And all that I did there was split the fraction so that I used the left side and I used the right side separately. And that's only possible if there's one thing in the denominator. Alrighty, so now that I have it broken into 2 things, I can see this piece right here as, its own separate identity. And 1 over cosine squared is secant squared of x, and that's going to be minus this whole deal that's happening here. Now I can break this up one more time so that it says sine of x over cosine of x times 1 over cosine of x, right? If I multiply these 2 fractions together, I would come right back to this one up here. So what is sine over cosine? Sine over cosine is tangent, and what is 1 over cosine? Secant. So this is secant squared of x minus tangent secant. Tangent x times secant of x. And that's, as far as we really care to go. I could factor out one of the secants, but it really doesn't help me out at all. That's as far as we would go with that. The main important thing about rewriting from fractional form is this idea of multiplying by the conjugate. Once you multiply by the conjugate, the rest of it can kind of flow off of there if you recognize the identities. But this is the part that's a little bit different, multiplying by the conjugate of the denominator. Alrighty, I think that's it. Yep, that's it for today. That's 5.1. I know there's a lot of information there. It's going to take a little while for everyone to become masterful or even proficient in doing this, but it is. Once you get a hang of it, it starts to become pretty fun. Do the assigned exercises as you know. I will see you in class. We can clear everything up. Peace out.